Hey guys, welcome to our first pre-calculus lesson. Today, we're going to talk about relations and functions, and we're going to get into domain and range of functions. But first, let's start with some definitions. A relation is a set of ordered pairs. So for example, I could have the ordered pair 1, 3, 2, negative 5, 3, 7, and we'll just cut it off at those three. So there's a relation. It's just a set of ordered pairs. A function is a specific type of relation. So a relation can be a function, but it doesn't have to be. A function is a relation. It's a relation in which each x value has only one corresponding y value. So if you look at the relation I have up here as an example, 1 only has a y value of 3. You don't see 1 showing up again as an x value with a different y value. 2 only has a y value of negative 5. 3 only has a y value of 7. So this is a function. But if I added the pair 1, negative 4, now it's not a function anymore because the x value 1 has two different y values, 3 and negative 4. So now it's not a function. So it's a function if each x value has only one y value. It's not a function when one of the x values has multiple y values. Okay, so domain of a function or a relation is the set of all possible input values. Okay, and those input values are just the x values. The range is the set of all possible output values. And those output values are the y values. Okay, so domain is all the x's and range is all the y's found in a relation. And remember that relation may be a function, may not be a function. So in number 1, we want to write this relation right here as a table of values, then as a graph, and then we want to state the domain and the range. So a table of values can be done in different ways. I'm going to do mine as a t-chart. So the ordered pairs are 2, 1, 3, 3, 0, negative 3, negative 1, negative 5, and negative 2, negative 7. Okay, so there's my table of values. All the x values, all the y values. Then it says a graph. So I'm going to plot all of those points on this graph. So there's 2, 1, 3, 3, 0, negative 3, negative 1, negative 5, and negative 2, negative 7. Now I shouldn't connect those as a line because this says that my function or my relation is just these 5 points. It's not everything between them, it's just those 5 points. When I write the domain, I'm writing the set of all the x values. Typically that would be done in numerical order. So it's the set that includes negative 2, negative 1, 0, 2, and 3. All of the x values. The range is the outputs, and that's all of the y values. That is the set that includes, in numerical order, negative 7, negative 5, negative 3, 1, and 3. So there's my domain and my range. Now before we move on, I want to consider whether or not this is a function. And this one is a function because no x value is repeated with a new y value. And another thing to think of is this, is what's called the vertical line test. There's no place on this graph where I could draw a vertical line and actually touch two different points. So this is a function. So I'm going to make a note here by number 1. That one is a function. Number 2, we are asked to graph this equation and then give the domain and range. So it's got a y-intercept of -3 and a slope of 2. So that's positive 2 over 1. So that means we're going to go up 2 and over 1. And when we graph a line, we shouldn't just say, all right, I've got my 2 points make a line, that's good. So we don't want to do that. So what we need to do is continue following that slope up 2 and over 1 as many times as we can before we run out of room. And then to maintain a positive slope, we can go negative, negative, so down 2 and left 1 until we've filled up the entire graph. And now I know when I connect these that I've maintained the proper slope all the way through that line. I guess I did miss a little bit up here. So the domain and range. The domain is all of the x values, which is left to right. So if we consider this graph going left to right, on the left, it's going to continue moving left forever. And on the right, it's going to continue moving right forever. And it's never going to miss a point left to right. So it goes infinitely left, infinitely right, touching everything along the way, which means the domain is all real numbers. And there is a shorthand for that. It's this symbol. So that symbol says all real numbers. Okay, so we can just use that symbol from now on to tell that it's real numbers. So then the range is up and down. It's the y values. As it goes up, it's going to go up forever. It's going to go down forever. It's not going to skip any y values along the way. So the range is also all real numbers. There is no place where I could draw a vertical line that is going to touch this graph in 2 points. So number 2 is a function. Every x value has only one y value. Every input has only one output. So for 3 and 4, given that x is an integer, state the relation representing each equation by making a table of values. So I'm going to have a chart of x and y. Then graph the ordered pair, and then we're going to tell the domain and range, and we're going to decide whether or not it is a function. Okay, so given that x is an integer, this right here is the equation of a line. However, if I actually graph it as a line, like that, then I've used all the decimal or fractional values between points, and that includes more than integers. So I'm not going to be able to connect this and make it a line. I'm only going to be able to plot integer coordinates. And I'm only going to be able to plot integer coordinates on that interval. X's that are greater than -2, greater than or equal to -2, but less than 3. So the smallest number I can use is -2. Then I can use -1, 0, 1, 2. I can't go any farther because its x is less than 3, not less than or equal to. So it can't be 3. So 2 is the greatest integer I can use. Then I need to plug all these x values in. So those are my inputs. I'm plugging them in and finding an output, a y value. So I'm going to plug in that -2. Opposite of -2 is 2 plus 2 is 4. -1. Opposite of -1 is 1 plus 2 is 3. Opposite of 0 plus 2 is 2. Opposite of 1 plus 2 is 1. And the opposite of 2 plus 2 is 0. So those are all the coordinates that I need to plot. Negative 2, 4. Negative 1, 3. 0, 2. 1, 1. And 2, 0. So those are the only 5 points on this graph. The domain is all of the x values, the set that includes negative 2, negative 1, 0, 1, and 2. And the range is all the y values, the set that includes 0, 1, 2, 3, and 4. And you'll notice that none of these x values is repeated with a new y value, and that you can't draw a vertical line anywhere on here that's going to touch 2 or more points. So number 3 is a function. Then number 4, absolute value of y equals 2x. You may have seen this before, maybe in Algebra 2, and I'll remind you that this gives 2 cases, and I'll write the 2 cases and then talk about why. So the first case is y equals 2x. The second case is y equals the opposite of 2x. And here's why that is. If I substitute 2x in for y, so this 2x goes right here. The absolute value of 2x is 2x. But also if I substitute a negative 2x in for y, the absolute value of negative 2x is also positive 2x. So y equals 2x and y equals negative 2x are our 2 cases. And we're given this restriction, x equals 3. So if x is 3, and I plug that into the first equation, y equals 2 times 3, my output is 6. But also if x is 3, and I plug it into the second equation, negative 2 times 3 is negative 6. So I get the 2 points, 3, 6, and 3, negative 6. The domain is 3. I don't have to list it twice just because I've used it twice. It's the same number, so the domain is 3. That's the only x value used. The range is negative 6 and positive 6. We'll notice for 2 reasons this is not a function. So the first reason is I can look right here and see 3 is paired up with a 6, 3 is paired up with a negative 6. Okay? The second, and it's really the same reason, it's just a different test. It's the vertical line test. If I draw a vertical line right there, that same line is going to touch 2 different points. So this one is not a function. It is a relation, just like all the others, but this relation is not a function. On number 5, for all 3 of these graphs, we're going to decide whether or not they are a function. We're also going to find their domain and their range. So let's do domain first on this one. Left to right, this is going to go infinitely in both directions. It doesn't skip anything, so the domain is all real numbers. When you think of it as up and down, it's also going to touch all real numbers vertically. So the y values will be all real numbers also. So the domain and range are both all real numbers. There is no place on here where I can draw a vertical line that's going to touch 2 different points on the graph. So yes, this is a function. On the second graph, left it's going to go infinitely, right it's going to go infinitely. So my x values, the domain is all real numbers. It's going to go up forever. It's going to go down forever. So it's going to touch all y values. The range is all real numbers. Is it a function? The answer is no. because of this shaded region down here, this isn't a linear equation, it's a linear inequality. So this would be less than or equal to. So that means every point in here, whether it's an integer point or not, is part of this graph. So when I draw a vertical line, once I get right here, I'm now touching an infinite number of points with that same vertical line. No, this is not a function. For the last graph, to the left and right, I've got two arrows here and here that are both going right. This is going pretty hard right. This one not so hard, but it's still going right. So that means it's not going to come back this way forever. Now, if there was an arrow that did that, I would say, yep, it's going to come back to the left forever, but it's not. So the farthest it goes to the left is right here at -3. So the domain is all x's that are greater than or equal to -3. Vertically, up and down, the y values, it's going to go up forever, it's going to go down forever. The y values are all real numbers, so the range is all real numbers. Is it a function? Well, right here I drew a vertical line that only touches at one point, but it is possible to draw a vertical line that touches more than one point. So no, this is not a function. For 6 and 7, we're going to deal with function notation a little bit and how to substitute in a function, how to find the value of a function for a given x value. So here, find the value of f of 3 if f of x is 5x squared minus 4x plus 1. That means for f of 3, I need to substitute a 3 in for all the x's. So that's 5 times 3 squared minus 4 times 3 plus 1. By order of operations, I have to do the exponent first. So that's 5 times 3 squared is 9, minus 4 times 3 plus 1. Now I need to do multiplication. So that's 5 times 9 is 45. 4 times 3 is 12. And then I do addition and subtraction. They have the same priority. That just goes left to right. 45 minus 12 is 33, plus 1 is 34. So f of 3 has a value of 34. In number 7, find g of n plus 3. So that's g of n plus 3 equals 2x squared. So I'm going to take this n plus 3 and put it in for x. So that's 2 times n plus 3 squared. Okay, there's kind of a shortcut that we can take to do n plus 3 squared. Anytime you're squaring a binomial, it's the first term squared plus double the product of the terms. So 3 times n is 3n. That's the product. Double that is 6n. And then the second term squared is 9. If you're good with shortcuts, go ahead and do that. First term squared, double the product of the terms, second term squared. Or you could expand it. It's 2 times n plus 3, and that squared means times itself, so times n plus 3. If I distribute these, the n and the 3, n squared plus 3n plus 3n, that's where we get the 6n, and 9. So either take that shortcut or distribute, so we'll expand and distribute. Sometimes when you try to take a shortcut, you miss that middle term. So if you're good with that shortcut, do it. If not, expand it and distribute. So then we're going to distribute that 2. 2n squared plus 12n plus 18. Now we are going to find the domain of a function from an equation written in function notation. So there's 2 hints. The first hint is that a denominator can never, ever, ever equal 0. So what we need to look for is whether or not there's a variable in a denominator. In number 8, there is a variable in a denominator. So we need to say that that denominator, 11 minus x, cannot equal 0. So I'm going to move this negative x over to the other side, and I'm going to get x cannot equal 11. The other hint is that what you find underneath a radical cannot be a negative number in the real number system. So I need to look to find a variable under a radical. And in number 8, I do not have a variable under a radical, so hint B will not apply. So my domain is all real numbers except that x cannot be 11. In number 9, hint A, a denominator cannot be 0. I do not see a variable in a denominator. And it's not even just do I have a denominator, it's do I have a variable in the denominator, and I do not. Next is hint B, under a radical cannot be a negative. Here's something underneath a radical. Now, not negative means that its relationship to 0 is that it is greater than or equal to 0. So this underneath this radical, 2 plus x, has to be greater than or equal to 0. So when I move that 2 over, I get that x has to be greater than or equal to negative 2. So x can be negative 2. 2 plus negative 2 is 0. Under a radical, that's fine. But anything smaller than negative 2 is going to give me a negative under that radical. And in the real number system, that does not work. So my domain is all x's greater than or equal to negative 2. And number 10, I do have a variable in a denominator, so hint A applies. So this entire denominator, the square root of x, cannot be equal to 0. So I'm going to go ahead and solve that by squaring both sides. So x cannot equal 0 squared is 0. X cannot equal 0. Hint B is that what's underneath a radical cannot be a negative number. So that under the radical, that x has to be greater than or equal to 0. And there's nothing to solve there. So my domain is x has to be greater than or equal to 0, but x cannot be 0. So I have to take that equal to part out. X is greater than 0 is my domain. So in this last problem, I have a denominator with a variable in it, so hint A applies. I do not have a radical with a variable under it, so hint B does not apply. So this denominator, x times x squared minus 4, cannot be equal to 0. So I'm going to go ahead and factor this x squared minus 4, and that is a difference of squares, and it factors to x plus 2 times x minus 2. Okay, and if you don't recognize that difference of squares, put in a 0x. So you have x squared plus 0x minus 4. What multiplies to negative 4 and adds to 0? Positive 2 and negative 2. Think about this also. X plus 2 and x minus 2 are conjugates of each other. When you multiply conjugates, the middle term cancels out. You've got a minus 2x and a plus 2x. Gives you 0x. Cancels out. So difference of squares will multiply to, or will factor to, a pair of conjugates. So what makes this factor equal 0? If I put in a 0 for x, this factor will be 0. If I put in a negative 2, this factor will equal 0. And if I put in a positive 2, this factor will equal 0. So there are three things that x cannot be. So x can be all real numbers. Let me get rid of that and say the domain is all real numbers except x cannot equal 0, and it can't equal 2 or negative 2. And if we want to go shorthand with that, we can do plus or minus 2. So 0, positive 2, and negative 2 are what x cannot be.